welcome back everybody. So we're now going to look at polar coordinates from the parametric point of view as well as finding derivatives. So we'll just note last time we looked at polar coordinates and what polar curves look like in general. Just a bit of review from our previous classes. We'll spend some time constructing some of these graphs as well. Graphing the polar equations is going to be important for this section. And note we looked at how to switch coordinates, how to locate coordinates, etc. So today we're going to look at how we can apply polar coordinates as parametric equations and then compute their derivatives. So in other words, if we have a polar equation of some kind, maybe a cardioid. So R equals A plus A. This would be sine theta. So if I have this polar curve, then everywhere at this polar curve, if I take any particular point, there could be a tangent line with a slope. And so we might want to know what the slope of that line is. But now it's going to be, R and theta are our two measures. Note, theta is actually kind of everywhere here. R is the distance, right? So the rate of change of R with respect to the angle measure is going to be what we look at. We'll draw it all the way there. So dr d theta is going to be a calculation for us, but we know that this curve can be written in terms of x and y, where x is r cosine theta and y is r sine theta. So there's a representation we can use with x and y in terms of r and theta, which means that we can convert this using derivatives to get dy dx. So our normal tangent line slope that we think of in terms of x and y. So that's what we need to build for this portion. And what we'll note is that x equals r cosine theta and y equals r sine theta, our representation of those polar coordinates in rectangular form, are parametric equations, right? These are parametric equations with theta being the parameter. So our parameter is theta. R is going to be a function of theta as well, right? So note when we write our polar equations, R is going to equal some values with theta in them, where theta is the changing quantity. So R is a function of theta, which means that we really have just a single variable expression here. R is a function of theta, cosine of theta is in terms of theta. So this r cosine theta is just a product of two functions of theta. But because it's a product, that means if we want to know the derivatives parametrically, say dx d theta or dy d theta, we have to use the product rule. So we'll note for dx d theta, we'll differentiate r first with respect to theta. So we'll have dr d theta times cosine theta plus, now r times the derivative of cosine, but the derivative of cosine is negative sine, so we'll get minus r sine theta. And then for dy d theta, we'll do the same thing. So we'll have dr d theta sine theta, and then plus r cosine of theta. And those are the same sorts of derivatives that we discussed before when we were doing dx dt, dy dt. So all the same rules are going to apply for finding dy dx. Which means that dy dx is equal to dy d theta divided by dx d theta, which are, these longer expressions that we're using the product rule for. So that's what we're going to do for slopes. One thing we'll note, what we can also do, so for example, if we know that r is equal to, let's say, 2 plus 2 sine theta, then if x is r cosine theta, before we take our derivative, what we did above, we can substitute in r to begin with. So we could rewrite this as 2 plus 2 sine theta times cosine theta, which would give us 2 cosine theta plus 2 sine theta cosine theta. And then we can differentiate once we've distributed, and this will sometimes be a little bit cleaner and a little bit nicer. And in particular, what we'll notice is a lot of these combinations will give us identities. So for example, in this case, this would be sine of 2 theta. And in other cases, we'll get cosine of 2 theta or some sort of multiple angled representation. So you can start simply from cosine and sine theta and work it out that way, or you can distribute out whatever r is in terms of theta into your general expression and then differentiate from there. And the other thing that I'll note too is that this may look kind of messy because it's a longer expression, and so I wouldn't recommend memorizing this. All you need to go from is those first representations of the parametrics. So start there, differentiate if you need to get these expressions, or again, just distribute out and then differentiate with respect to theta as you normally would think of differentiating with respect to a variable. All right, so let's get to the notes themselves. So on the front here kind of has exactly what we've just discussed, that our polar coordinates are really parametric equations when we're thinking about our graph of r equals f of theta. And so we get those two product rule representations for dx d theta and dy d theta. And then again, we can combine here. Where this is going to differ from our previous parametric equations, which involve polynomial functions, square root functions, exponentials, is that sine and cosine are periodic, meaning we're going to get repeated values. So in most cases, we're going to want to consider the period or the domain that we need to get all of the values that describe our curve. So let's go ahead and get started with the first example. So it said find the points on the curve, r equals cosine theta plus sine theta, where the tangent line is horizontal or vertical. So we're going to find when dx d theta, so note, and dy d theta are equal to 0. So same as when we would do this with parametrics in terms of t, we want to know when the numerator denominator of our derivative for the tangent line is going to be 0. And note, we want these to not simultaneously be 0. So we still need to compare them with each other. And any overlapping values will just simply be undefined, which is probably going to represent some sort of a cusp. All right, so let's go ahead. And first, we can kind of think of the graph of cosine theta and sine theta. So if you plot some points here, what you'll get is just noticing if it's r equals cosine theta, that would be a circle over here. If it was just sine theta, it would be a circle over here. So what this sum is going to do is going to add the two sets of coordinates together. And what we're going to get is a circle that is shifted. So it's shifted in the plane here a little bit. But it's still going to end up being a circle. And we could work out maybe where the coordinates are, etc., by eliminating the parameter and turning this into a rectangular equation. But what you'll notice is that that's going to be pretty messy. So we'll just go ahead and work from our definitions. So we have x is equal to r cosine theta, which for this example, I'll substitute in. So I'll substitute it in and we'll see what that looks like. And then maybe the next example will work from that product rule representation. So r cosine theta is going to be cosine theta plus sine theta, all times cosine theta, which is going to be cosine squared theta plus sine theta cosine theta. Okay. And then y is r sine theta, which is cosine theta plus sine theta quantity times sine theta, which is going to give us almost the same expression, just with sine squared instead. All right. And again, what we can note here, something that's going to pop up quite a bit, is this sine theta cosine theta expression, which in this case, because the coefficient is 1, is going to be 1/2 sine 2 theta, which means the derivative of that is going to be simply cosine 2 theta. But let's go ahead and operate as if we don't recognize that identity. So we'll just use the product rule. All right, so let's go ahead and compute those derivatives. Oops. So we'll do dx d theta. So we'll take the derivative of cosine squared. So that's going to be -2 cosine theta sine theta using the chain rule. And then plus, so then we'll use the product rule here. So derivative of sine is cosine, so we'll have cosine squared, and then minus sine squared theta, which again, cosine minus sine squared is going to be cosine of 2x. So now we'll rewrite this for simplicity. So we're going to have negative sine 2 theta, since that is sine 2 theta, and then this we'll rewrite as cosine 2 theta plus cosine 2 theta. And we could reverse the terms too to make it cosine 2 theta minus sine 2 theta. And then dy d theta is equal to, so now we're going to get the first part, cosine sine, is going to give us the same thing that we got before, which is going to be cosine squared theta minus sine squared theta. And then plus, the derivative of sine squared will be 2 sine theta cosine theta, which is almost the same, right? So again, we've got cosine 2 theta, sine 2 theta. So what we're going to end up with is cosine 2 theta plus sine 2 theta. So we're only going to be off by a sign here between our numerator and denominators. All right, so we're not finding dy over dx, so we don't need to take the ratio of these. We can just consider each one of them separately. So we'll start with a horizontal case. So that'll be dy d theta is equal to 0. So that's going to be cosine 2 theta plus sine 2 theta equals 0. And then on this side, we can put the vertical case. That's where dx d theta is going to be equal to 0. And that's going to be cosine 2 theta minus sine 2 theta equals 0. All right, so let's go ahead and work these out. So for the horizontal case, we could think of this as sine 2 theta is equal to the opposite of cosine 2 theta, and then we could divide by cosine 2 theta. Because if we get tangent, that might be easier to work with, so that we only have one trig expression. So we'll have tangent 2 theta equals -1. And one thing to note here, our original function was in terms of 1 theta. So we're going to consider theta between 0 and 2 pi, since that's 1 period. So then for 2 theta, we double the size of our domain, but we're actually going to get all of our solutions between 0 and 2 pi. So we'll take the arctan of both sides. So 2 theta is equal to arctan -1, which is going to equal a bunch of angle measures. So let's see what it's going to be. So note arctan is going to be -1 in the first and fourth quadrants at the 45-degree measures there. So that will be 3 pi over 4, 7 pi over 4. And then if we add 360, so 8 pi over 4 to each one of those, we'll get 11 pi over 4 and 15 pi over 4. And then we'll divide by 2. So we'll divide all those by 2. So theta is going to equal 3 pi over 8, 7 pi over 8, 11 pi over 8, and 15 pi over 8, which are all between 0 and 2 pi. So those will be our 4 solutions. Note, we could actually kind of go infinitely since we haven't been given a domain for theta, and there's actually an infinite number of values where the slopes will be that, but these will be the 4 that we'll use for our solution here. All right, so for the vertical case, we'll do the same thing. So we'll get cosine 2 theta equals sine 2 theta. If we add sine to the right-hand side, then again we'll divide by cosine 2 theta. And then we can rearrange this as tan 2 theta is equal to now positive 1, and then we can take arctan of both sides. So what we'll get is now all of those first and third quadrant angles. So we'll get pi over 4, 5 pi over 4, and then we'll add 2 pi. So we'll get 9 pi over 4 and 13 pi over 4. Yes, and then we'll divide by 2. So theta is going to equal pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. So we'll check those values against each other, but we know actually arctan and tangent is negative and positive in 2 different quadrants. So these are not going to be overlapping, so we don't have to cancel any of these out. These will be all the locations where our tangent line to the curve will either be horizontal or vertical. And then graphically, we'll know that those values are going to be, whoops, at the exact sides of the circle that are perfectly horizontal or perfectly vertical. All right, so let's go ahead and move on to the next example. So now we'll find the dy dx value, so the slope of the tangent line to the curve at theta equals pi over 3. So we've got r here. For this example, I will go kind of the product rule route just to show you what that looks like. But again, we could just substitute r in if we wanted to. So x equals r cosine theta. And again, we could substitute r in and then differentiate, but I'll just note our product rule representation. So dr d theta cosine theta minus r sine theta. What we should note here, however, make this in a slightly smaller font, is that dr d theta is equal to negative cosine theta. So we'll want to know what dr d theta is since we need to substitute it in into our derivative expressions for dx d theta and dy d theta. So y is r sine theta. So dy d theta is equal to dr d theta sine theta plus r cosine theta. Okay, so now we can substitute values in before we write our dy dx term. I would recommend that just to clean everything up to begin with and then write your ratio, because you can get some nice symmetries or nice cancellations possibly. So dr d theta is going to be negative cosine theta times cosine theta, so it'll be negative cosine squared theta, and then minus r sine theta, which is going to be 2 minus sine theta times sine theta. And then for dy d theta, we'll get negative cosine times sine plus, and then 2 minus sine theta times cosine theta. All right, so let's clean these up a bit. So this is going to equal, so now we need to distribute the negative sign as well as the sine theta to each term. So let's do that. So we'll have negative cosine squared theta, so minus 2 sine theta. and then plus sine squared theta, which then we can rewrite sine squared theta minus cosine squared theta minus 2 sine theta. Okay, so let's see. And then for our y term, we'll do the same thing. So for dy d theta, we get negative cosine theta sine theta plus 2 cosine theta, and then minus sine theta cosine theta. So these two can combine, and we'll just get 2 cosine theta minus 2 sine theta cosine theta, which we can just write as sine 2 theta. All right, so that's dy d theta for us. What we'll note here is that this is the same as negative cosine 2 theta, right? So if we factored out a -1 from each term, we would get a negative there. We don't have to do that, but it might be something that makes it a little bit easier to calculate with. So either way, totally up to you. All right, so let's go ahead and find dy dx at theta equals pi over 3. So dy dx is going to equal our dy d theta term, so 2 cosine theta minus sine 2 theta over, and then I'll rewrite this as negative cosine 2 theta minus 2 sine theta. So then theta equals pi over 3. That's going to equal, so we'll have 2 cosine theta at pi over 3 is 1/2 minus sine of 2 times pi over 3. So that's going to be sine of 2 pi over 3, which is just rad 3 over 2 still, positive. So we don't have a sign change there. All over negative. So cosine of 2 pi over 3 is negative 1/2. So we'll make that positive 1/2, and then minus 2 times radical 3 over 2. So we'll just note we can write this as 2 minus rad 3 over 2 over 1 minus 2 root 3 over 2. And then we can reciprocate and cancel those denominators. So then our final answer will be 2 minus rad 3 over 1 minus 2 rad 3. And that'll be our slope at pi over 3. And note we could go further and find the actual tangent line equation. In order to find the tangent line equation, we would use theta and r to solve for our x values. All right, so let's go ahead and look at number 3. This one's a slightly more interesting example because we have r squared now instead of cosine 2 theta. So what we should note here that is going to be important for these types of curves. So note this is a lemniscate, which means it's a figure 8 shaped graph. And because it's cosine, it's going to be symmetric about the polar axis. So it's going to look like this, and its radius will be 1, -1. So, okay, so our graph is going to look like that, and we want to figure out at pi over 6. So pi over 6 would be somewhere, maybe there. And then 2 pi over 3 is going to be somewhere up here. What is the slope of the curves at those points? We have to be slightly careful because it's actually cosine 2 theta in our expression, so it's going to be a little bit trickier to identify exactly where the line is located, but we'll go ahead and try. All right, so for this expression then, we'll just note we've got normally x equals r cosine theta. But we don't know what r is nicely, right? So like r is the square root of cosine 2 theta, but we're not going to want to use that square root. We're going to want to kind of leave it as is for this example. So what we're going to do then is before we look at x, we're going to figure out what dr d theta is. So dr d theta, oh, whoops. We'll start with our r squared equation, and we'll differentiate with respect to theta. So on the left side, remember we're differentiating with respect to theta. R is some function of theta, but we're going to treat it as just r. So we're going to actually be differentiating implicitly. So we're going to write this as 2r on the left times dr d theta. And then on the right, we'll just have negative 2 sine 2 theta. We can do some cancellation here of the 2's, and what we'll get is that dr d theta is equal to negative sine 2 theta over r. And I'm going to leave this as is, and you'll see why in a moment, that we're going to get some nice cancellation that works out for this. All right, so let's go ahead and calculate for x. So x is r cosine theta. So dx d theta is equal to dr d theta cosine theta minus r sine theta. So for this, we can go ahead and work this one out first. So we'll have negative sine 2 theta cosine theta over r minus r sine theta, which we can then simply write as negative sine 2 theta cosine theta minus r squared sine theta all over r. And we could also check the two values of the angles that we're interested in, and those will show us that at those points r is not 0. So we do definitely want to make sure r is not 0 at the points we're interested in. But actually, if we do substitution, right, there's going to be an issue with theta equals 2 pi over 3. So I'll discuss that after we do the work here. All right, so then dy d theta will do the same thing. So y is r sine theta. So dy d theta is equal to dr d theta sine theta plus r cosine theta, which is going to equal, again, dr d theta is negative sine 2 theta sine theta over r plus r cosine theta. But that can be, again, simplified. If we find a common denominator, all over r. So when we take the ratio, then our r's are going to cancel out by reciprocation. Okay, so let's go ahead and keep working this way. So we'll write dy dx. So we want to know the slope of the tangent line at those 2 points. So let's go ahead and write up at the top. So again, our r's are going to cancel when we take the ratio. So I'm just going to write the numerators in. And what I'm going to do for the first part is to factor out a negative 1 for the not factor out a negative 1. We'll just write dy d theta. But I'm going to substitute in the r squared term. So r squared cosine theta becomes cosine 2 theta cosine theta all over, and then my denominator is going to be factoring out a negative 1. We'll have sine 2 theta cosine theta plus, and then cosine 2 theta sine theta. All right, and what you'll notice here is that both of these look like they are trig identities. And so why don't we rearrange these and clean them up a little bit. The bottom one, actually, we don't need to. we can see that this is it looks like a sandwich, right? So we've swapped the angle measures and we've swapped the trig functions. So we'll note that this is the same as sine of 2 theta plus theta, which is just sine of 3 theta. So we have sine of 3 theta on the bottom here. And on top, if we rearrange these terms, we'd have cosine 2 theta, cosine theta minus sine 2 theta, sine theta, which is an identity for the angle sum of cosine. So 2 theta plus theta. So that is really cosine 3 theta up at the top. We'll note we still have this negative sign on the outside though, so we're going to have negative sine 3 theta. So what we end up with that we can simplify that's going to make our calculation much easier is that this is really cosine 3 theta over negative sine 3 theta, which is simply negative cotangent 3 theta. All right, so let's go ahead and compute our three values then, since we've got a pretty simple calculation here. So if theta is equal to pi over 6, or theta is equal to 2 pi over 3, we'll get negative cotan. 3 times pi over 6 is going to be pi over 2. And then here we'll have negative cotan. We'll note this is our dy dx. We'll have negative cotan of 2 pi. Now cotangent is cosine over sine, so we'll get 0 over 1 for our first slope. So at pi over 6, on our graph here, that's actually going to be, horizontal. So that's going to be exactly horizontal. And if we look at 2 pi over 3, well, that's not going to exist. It's going to be approaching infinity, or if we take the limit as we approach that value. And this is going to be because our lemniscate has a very specific domain. So we'll get 0 and does not exist. But what we'll note here, if we go over to the note, if r squared equals cosine 2 theta, r squared is always positive, and cosine 2 theta is going to be the graph of cosine, but with the period cut pretty significantly. So what we'll note is that we can't have any of these values where we get a negative output, which means that we're going to be stuck between 0 and this is pi over 4. And then this will be 3 pi over 4 to pi for the first period. So our domain then is going to be 0 to pi over 4 union 3 pi over 4 to pi. And we'll note that in here is 2 pi over 3, that angle measure that we were looking for. So, so just be careful of domains of polar coordinates. And this will just come from maybe practicing with graphing as well. So that concludes our notes. So if you do have questions, let me know. Come by the office hours or shoot me an email. And until I see you next time.